Today, me and Elton will be talking to you about why Vin Diesel would make a terrible physicist and why he should never have a bank vault to do physics to. We're going to be watching the scene from Fast Five.
Hold it out, Mira. Got a straight shot for 2 blocks. Go right. Got it. Well, the plan's working. You guys have every correct copy on your tail. You guys have to move fast. What's the best route? You keep going straight another half mile and go up full circle, and then go left. That ain't gonna work. Spikes ahead, Mom. I got spikes. We're going right. Now it's too tight, not to fit. You got no choice now. Oh, shit. Guys, I'm hearing all this noise. Did you just take out a bank?
So, that's a lot of nonsense, and we're going to go into why. So, to find a very simple thing to look at, let's look at this very start of the sequence. And in this part, the vault and the cars are going in a straight line, the tension's pretty straight, very simple physics to look at for us to explain to you. The main components at play are friction, with the vault sliding against the ground. There's friction happening there. There's forces at play, and they're going over some distances, so work is another concept that we need to look at. And because we're doing this over some time, power is also another concept we're going to look at. And here's our force diagram of this scenario. As the vault is on a flat surface, our weight and our normal force are the same value in opposite directions, and our friction force and the combined tensions of the two different cables to the cars are equivalent. So the tension 2T equal F, F for friction.
Now we need to calculate the friction force. And we know that the friction force is equal to the coefficient of friction multiplied by the normal force. To find the normal force, we'll look at the force diagram where we can see that since the bank vault is not accelerating upwards or into the ground, the normal force is equal to the weight of the bank vault. And so we can say that the friction force is equal to the coefficient of friction multiplied by the weight of the bank vault. We found that the coefficient of friction between asphalt and metal is around 0.47, and that the mass of the bank vault is approximately 10,160.5 kilograms. And if we were to multiply 9.8 multiplied by the mass multiplied by the coefficient of friction, we get a friction force of approximately 46,800 newtons. And with that friction force, we can then calculate the work done on the bank vault by the cars. And we calculated the distance based on traverse lines on a crosswalk, and we found that it's approximately 1.8 meters, and that would be our distance. So we would multiply the friction force times the distance, which would give us a work of approximately 84,238 joules. If we look back at the scene, we'll see that the bank vault took 0.4 seconds to cross both transverse lines, and with that we can calculate the power, since we know that work over time is equal to power. And so we'll plug in our previously calculated work divided by 0.4 seconds, and we get a power of around 210,000 596.684 watts. And with the wattage, we can then find how much horsepower is required for each car to pull the bank vault when it's moving at a constant velocity. So we'll divide our power by 746 and divide it also by 2 in order to find the horsepower for one car. And we found that to be 141.151 horsepower per car required to move the bank vault at that velocity. And since we have the required horsepower, we can prove if this scene was possible or not. And we found that this scene's possible because the maximum horsepower of a Dodge Charger SRT8 model made created in 2010 outputs around 425 maximum horsepower, and we only need 141 horsepower per car. Thank you for listening. Do you have any questions?